All right, I want to talk to you for just a couple minutes about cylinders, pistons, and all this crazy stuff going on. Now, what we're using as an example is an automotive engine. I'm aware of that, fortunately, but I want to point out a couple critical differences, but it actually is a little bit easier to see what's going on an automotive engine. So what we're looking at right now is the top end of the engine with the camshafts removed. So you can see all of the valves and the valve springs on the exhaust side and the intake side. And normally you'd see two camshafts. It's a dual overhead cam, so you'd see two camshafts sitting over top, which directly actuate the valve operating mechanisms. And then over here we have a distributor and a crankshaft position, or sorry, a camshaft position sensor. These sensors you don't see on aircraft engines as much, but you do tend to see things very much like a distributor in the form of a magneto. In fact, a magneto has a distributor on it. The only difference is instead of taking power from a battery, it generates its own power, which you'll be learning about this quarter as well. Anyway, as we peel back the layers of this onion here, we're going to remove the cylinder head from the crankcase so you can see what's going on inside. So I'm just going to wiggle this out of the way real quick. Yeah, it's heavy. There we go. And set it off to the side. So what you can see now, we've exposed where you can see the pistons and the cylinders inside the case. Now, this is something that is common across different engines, which is the case is made out of a much softer material than we would normally need for these pistons to be able to run. These pistons move very fast inside the engine. They operate in a largely destructive process, the way that the piston rings move against the cylinder wall. And again, they reach very, very high speeds, all of which does not help durability in the long run. So if we just had aluminum cylinder walls, we'd have a major problem. But if I get a little bit closer, what you can see here is there's actually a difference in color between the aluminum that makes up the jacket liner and then the actual cylinder wall material on the inside. And this is very, very similar to what we see in aircraft reciprocating engines, where you have a barrel which is made out of machined aluminum or machined steel potentially, and then there's a case hardening process that is taken to create a much harder, tougher, more durable surface on the outside. And that's exactly what we see in this case. We have this different color liner, and in fact, on a lot of automotive engines, that liner can be pressed out at a machine shop and you can insert a new one. It isn't really that convenient with aircraft cylinders. We'll get a little bit more into cylinder overhaul later on, but effectively, in some cases, we have a couple tricks like chrome plating or oversizing the cylinder bore to be able to deal with abnormal wear or excessive wear. The other thing I want to point out to you is, again, a little bit different from what we see on a typical aircraft reciprocating engine, but it is similar enough to be able to get the point across, and that is where we have the piston move versus where we have the valves move. In both cases, the piston is only going to travel inside of the cylinder. It's not going to go up into the combustion chamber. It's only going to travel within the cylinder barrel. On an aircraft engine, the cylinders would be outside of the crankcase. So instead of having them inside the crank like we see, they'd be bolted onto the outside. It's a more efficient design, especially if we're going to be air cooling. And it's very similar, if we were talking automotive terms, to a boxer engine. Kind of slick, but anyway, I digress. Our cylinders are on the inside in an automotive application. On an aircraft engine, they are outside. But each cylinder is still made up of two parts: the barrel, where the piston's going to travel, and then the head, which houses the combustion chamber. Which again, if I turn this over just a little bit, you can see pretty well right here we have our combustion chamber where the spark plug is housed, along with the valves, some very cruddy, dirty, nasty valves at that, on both sides. Now, again, this differs somewhat. This is a 16 valve configuration. So we have 4 valves across 4 cylinders. Aviation engines are typically only going to see 2 valves, one for intake and one for exhaust, and they are considerably larger, about twice to almost 3 times the diameter of these little valves you see here. Substantially larger, a lot more airflow moving through. But the concept is the same. We have the head versus the barrel. The difference is with a aircraft cylinder, this head actually has a threaded portion that the barrel screws into. So when they assemble those on aircraft cylinders, they heat up the head, which again is made out of cast aluminum. Once it's totally heat soaked, it expands enough that they can screw in the barrel into that threaded portion, and that is what holds it together. So when the cylinder head cools back down, it shrinks, and now it has an interference fit on that cylinder barrel, and it shouldn't let go. The only caveat to that is if a crack develops where that thread portion is on the head, you can actually let the threads loosen up, and it can cause separation between the cylinder head and the cylinder barrel, which is kind of a big problem. We'll talk about that more when we get into overhaul procedures and why we would take an aircraft engine out of service. But that's what we're looking at. We have our barrel portion, we have our head portion. This is where our valve mechanism is going to have room to operate. This is where the piston is going to travel up and down. And when we calculate the displacement of an engine, we have the displacement of our piston moving from bottom dead center all the way to top dead center. Effectively, we're talking about how much space is displaced by the piston as it moves. When we talk compression ratio, we're talking the volume of the cylinder when the piston is all the way at the bottom, as opposed to when the piston is all the way at the top. The difference in those two sizes. The only factor that throws people off is instead of just talking about what happens in the barrel, we also have to account for the volume that's up here in the combustion chamber, and that's how we accurately determine the compression ratio of an engine. Hope you enjoy this brief little run through on cylinders and what's going on inside, and we'll look forward to seeing you on the next video.